So, if you remember, the way we defined our delta theta was going to be some alpha times some dou rho by dou theta, right, or dou eta by, we defined it as dou eta by dou theta, right, where eta was some performance measure, right. So, one popular performance measure that we could have is essentially the average reward, which is right. So, limit n tending to infinity of the sum of r1 to rn, and we did this last time. I put the n within the expectation, right. Now I have taken the n outside the expectation, otherwise it is exactly the same expression I wrote in the last class, right. For this is the average reward, right. So, one way of thinking about the average reward is that it is given by the following where RSA is the reward you get for taking action A in state S, right. So, what have I done here? I have marginalized over S prime, I just summed over all S prime that you could land up, right, just to make it easy. You can always write an extra summation here over S prime and keep carrying it around, right. So, RSA is essentially so using our old notation. So, this is what RSA is. If you want, you can write this summation inside that and you can keep carrying it around. I just want to simplify this, I put in a new notation for that summation, okay. So, RSA is that, okay. And I am also going to define, without giving you any reasons for it, a new Q function Q pi SA for the average reward case, okay, which tells me if I start by taking action A, right, if I start by taking action A, so how much more than the average reward will I expect to get, right. There should not really be a difference, right, if you think about it. If I remove this difference and take the summation in, right, the summation over RT t equal 1 to infinity, summation over rho pi t equal 1 to infinity should be, looks like it should be the same, right. So, it looks a little counterintuitive, I am just pointing it out to you already, right, but then this is called the rho is typically called the gain of a policy, right, and this Q function is called the bias of a policy, okay. I think I got it right, I think that is the gain and this is the bias, right, and this can actually be used to compare different actions, right. So, if I start off by taking this action, so there will be some initial transient terms that might not get cancelled out, so that will tell me that I am slightly better than the other thing. So, this is why I said we need to do the whole couple of days of average reward RL, so that you can understand what is the difference between the gain and the bias and other things, but right now I am defining this without any further explanation. So, let us take this as the Q function definition for average reward RL, right. This essentially tells you how much starting off with action A, let us say A1 is better than starting off with action A2. It is more of a comparative value function that you should be using. Yeah.
Should it be divided by some kind of an n or anything?
Why not? Why?
Because if this action is very good and the rewards are always much higher than the rho, then the value will be a very high value, right, the summation. Won't that run into it?
How will that become how will that happen? Because this is pi anyway. I am behaving according to pi. I am just starting off with a, and after that I am behaving according to pi, right. So the long term behavior for R3 should be tending towards rho pi, right. I mean sometimes it is high much above rho pi, sometimes it should be much below rho pi, otherwise rho pi cannot be the average reward, right. After the first action I am always behaving according to pi, right. So it can't be the average reward, right. It is only the first action that is different, right. So if the first action gives me a slight advantage, then I am going to say that it is a better action than starting off with something else, okay. So it is essentially used as a comparative measure between actions. Okay. Does it make sense? Great. So likewise we could define a row for the discounted reward case also, right. If you remember, if I am going to use discounted rewards, what was the assumption I made for the policy gradient case? What is the assumption we made? S naught, right. There is one unique S naught, and I take the value of S naught as my value for the policy, right. So likewise I can define the same thing. I can look at the expected discounted reward starting from S naught, keep that as rho, and I can define my Q the usual way, starting from S naught, doing action A, following policy pi thereafter, okay. So that is my Q function, and I need dou rho by dou theta, right. So let us see what dou rho by dou theta should be. This was a pretty amazing result. So if you think about it, see pi depends on theta, right, all of you know, that is why you have the dou pi by dou theta, but d pi also depends on pi. So that should also figure in the derivative, right. Q pi SA also depends on pi, right, that should also figure in the derivative. So if you just think about applying the derivative directly to this expression, and essentially you will have to do it through the product rule, right. So there are 3 terms here and I should differentiate everything, but then it turns out that that is not really the case, right. And so derivative of rho by theta is, you just basically have to take the derivative of the policy with respect to theta and evaluate it at A, right, and basically you are done, right. This is an amazing result, right. So there are variations of these results already in the literature, but then this guy Peter Marbach came up with a proof for this, right. It runs into several pages, maybe 15 pages or 20 pages or something of his thesis. The proof of this theorem runs into several pages in his thesis, right. And then a little later, without really knowing about Marbach's result before they were set out to prove these things, so Rich Sutton, Satinder Singh, David McAllister and a bunch of people wrote this paper, and that is the proof, okay. So Marbach's proof runs for several pages because he was working from a different set of initial principles, and so Rich came up with this proof where he starts off with an expression that is completely unrelated to what they are trying to prove, right, and then somewhere along the line suddenly, like a magician, he derives this relation, okay. So I will show you this proof just because it is so elegant and so simple, and yeah, so all of you know what the expression for V pi is, do you? Okay, here is another expression. I am using pi of A given S and pi S comma A is the same, okay. So I can take the derivative of this right. So what will this be? Right. Yes, I mean that's rather straightforward. Okay, then what we do? Okay. So do we need to do anything to this first expression? Not really, that is what we want to be left behind, right. So we will just leave it as it is, right. We will just leave the first expression as it is, and we will play around with the second expression and see if we can make it go away. So why is it RSA? So the expected value of RT minus rho t, expected value of RT is essentially RSA, right. Where did we write RSA? So this is RSA, right. So that is the expected value I will get for the first step for taking action A, right. So expected value of RT will be RSA, then minus rho pi, and then what do we have? So where does that come? Right, it is t equal 1 to infinity. So this is like the first term, right. So this is the rest of the terms. Whatever follows later, I am writing it in terms of the value function, right. So this will go away because it does not depend on theta, right. So you will get minus Okay. Finally, we got our dou rho by dou theta. So far we did not have that expression at all, right. What we wanted to derive was dou rho by dou theta. So, I did not start from this expression, I am sorry, I did not start from, where is the rho expression, yeah, this expression I did not take the derivative, right. I started from some arbitrary equation, this is v pi equal q pi, right, and then I started making substitutions and then I took the derivatives. I finally got my term dou rho by dou theta. Now, I will have to rewrite it so that this comes to the left hand side. Okay. So, what do I get? Therefore, right. So, I think that is correct. I did nothing, I just took the dou rho by dou theta the other side. So, if you think about it, I multiply this by pi s a, right, but I can pull it out because it is not dependent on a and then sum over all a. So, that pi s a will go to 1, right. So, I will be left with dou rho by minus dou rho by dou theta. I bring minus dou rho by dou theta here, I take dou v pi by dou theta that side, right, and the rest of the terms I have written it like this. Okay. Is it clear? Okay. So, more sleight of hand now, right. So, I am going to take expectations with respect to d pi s on both sides, right. I am going to take expectation with respect to d pi s on both sides. So, essentially what that would be summation over s d pi s into rho of pi equal to summation over s d pi s into the first term summation over a Have I written it correctly? Right. So, the first term summation over d pi s, the second term d pi s, the third term d pi s. Okay. No. Okay, fine. Okay. So, this is fine, right. So, what you have done this. Now comes the amazing trick. Okay. So, we know that d pi s is a stationary distribution, right. So, let me just take this term alone, right, and write it like this. Right. So, what does this mean? Okay, I am going to start off with the stationary distribution S, I mean d pi, there is some state S. I will take an action according to my policy pi, then I will make a transition according to P. This whole thing, what do I expect this distribution to be like? Because d pi is a steady state distribution, the condition of steady state distribution is it should be the same, right. The condition when do you call d pi the steady state distribution, if I apply pi and p on it, I should get back the same distribution, right. Only then it is a steady state distribution. So, that is essentially what is happening here, right. If you think across all this summation over s prime and a, essentially I have applied pi and p on d pi, right. If I evaluate these two summations over this, I will essentially end up with d pi of s prime, right. So, this is essentially equal to summation over s prime okay. This looks familiar. Of course, I can ignore this because there is a probability distribution, it is 1, right. So, I can ignore this. So, basically I have the theorem dou rho by dou theta equal to summation over s d pi s into summation over a dou pi sa dou theta into q pi sa. Amazing, right. Whatever possessed them to start off with the equivalence between v and q to get this derivation on rho, right. Yeah, it never ceases to amaze me that that Rich managed to find something like this. Right. So, what is the nice thing is it gives you a good connection between using value functions and so, what is the difference between what we are doing now and what the motivation I gave you earlier? In the motivation I gave you earlier, you ended up using the V function. V was your baseline, right. When we said actor critic, so the actor was the policy, but the critic was V of S. Here the critic you are using is QSA, right. And the amazing thing is it turns out the same form holds regardless of whether you are using the average reward formulation like we did now or whether you are using the discounted reward formulation, except that you need to do a different sleight of hand to get the results, but the proof holds whether you are using average reward formulation or whether you are using discounted reward formulation, right. I encourage you to read the proof for the discounted reward formulation. So, I am without a TA, so you are my TA. So, just remind the TAs to put up this Sutton, McAllister, Singh and Kern, Mansoor paper online. Okay. So, I encourage people to read this. This is actually a really old paper, I think it is from 99 or something, but still it is amazingly instructive as to how you can think out of the box to get really simple proofs for things. Okay, this is one thing. So, it is now connected policy gradient approaches to the q value function. Okay, and we are still not done.